But if you put a negative angle, okay, so theta is equal to negative, let's say some negative angle that's equal to negative 34 and a half. Okay, negative 34 and a half, so that's going to be a certain city that has the latitude of LA, but it's below the equator. Okay, so I put negative 23 and a half over here. The number of hours sunlight, 8.41 hours. Okay, so in other words, it gives us a certain answer that's opposite to LA, right? If you add that to what was this answer for LA? 15.5 something. Okay, this answer for LA was 15.59. If you add them, you're going to get 15.59 plus 8.41, 24 hours. So the southern hemisphere should be exactly opposite to us. If we have more than 12 hours, they're going to have less than 12 hours. Then what's going to happen on December 21, it's going to switch. We're going to have less than 12 hours of sunlight. They're going to have more than 12 hours of sunlight. Now, how does this change as a function of the date? Okay, let's look at the position of the sun in the sky, the ecliptic. In astronomy, we learned that the ecliptic gives you the position of the sun. On March 21, on June 21, the sun is the highest in the sky. Then when the sun comes down, it's September 21, the sun crosses the ecliptic. The sun crosses the ecliptic on March 21 on its way up. And then it comes back down. On December 21, the sun is the lowest in the sky and it goes back up. Okay? So it basically kind of looks like a sine function. Okay? So roughly speaking, the sun crosses the ecliptic here March 21, this is roughly the 80th day of the year. We're going to do approximations here. January has 31 days. February has 28 days, except if it's a leap year. So I'm going to do approximations here. And March 21, so if you add 31 to 28 to 21, you have 4, 4, 8. So the March 21 is the 80th day of the year. So the angular position of the sun, theta 10 degrees, 20 degrees, 30 degrees. So the highest that the sun gets on the sky is 23 and a half. So the deck position of the sun is the vertical position in the sky above and below the celestial equator. So theta t, and this is the theta, the deck angle of the sun as a function of time, is equal to some amplitude sine of omega t plus phi. Okay? So this is the general position of any sine function. So we can approximate this like this. The highest angle that the sun gets is going to be 23 and a half. On June 21st, the sun is the highest in the sky at an angle of 23 and a half. Sine omega is how many days it takes the sun to make 2 pi radians. So that's going to be 2 pi divided by 365 and a quarter. Of course, it's not going to be exactly a quarter because it's a little bit more than a quarter, 2.256. But for now, let's just again make it simple. Just say 365 and a quarter. So it makes 2 pi radians in that many days, t. Okay? And the sun crosses the celestial equator at t equals 80 days. So we'll have here, this one we'll put brackets, t minus 80. Okay, so when t is equal to 80, you have 80 minus 80 is equal what? 80 minus 80, this thing is 0, sine of 0 is 0. And as the number of days are progressing, the days are going by, the sun's position, angular position is increasing, 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 until sine of this angle is going to be 1. It reaches a maximum angle of 23.5. And I multiply this by 24 hours. Now, what I'm going to do to simplify this is divide everything by Now what I'm going to do to simplify this is divide everything by cosine theta, divide this and divide this by cosine theta. So we end up getting like this. 1 plus sine theta over cosine theta is tangent theta, tangent 23.5. And then the 2 divides into the 24, you get 12 hours. 1 plus tangent theta, tangent 23.5. It looks cleaner, it looks quicker. The data that we used was the latitude angle of the city. The 23.5 was the inclination angle of the Earth. Now, what's going to happen is this. On June 21st, when the inclination angle of the Earth is exactly facing the sun, it's inclined at 23.5. The position of the sun in the sky is actually positive 23.5. Okay, as the days go by, the position of the sun on the sky changes. This 23.5 changes. So it's not always going to stay 23.5. The axis of the Earth will stay 23.5 like this. So it's going to go like this, like this, like this, like this, like this. It'll always stay 23.5. But as the days go by the time that the Earth is in September, the Earth's axis is facing this way. You look over at the sun's position in the sky is exactly in the middle. It's at crossing the celestial equator, right? So this 23.5 is exactly the deck angle of the sun. We can generalize it for any day of the year. So we could put this whole thing in here. So we'll have 1 plus tangent theta, tangent 23.5, sine of 2 pi over 365 and a quarter, t minus 80. So we have a general equation that works for any time of the year. June 21st, it's going to be, what's the t going to equal? T is going to equal, okay, you have 172. So June 21st is the 172nd day, approximately. So if you put that in here, when I put this in, and you put sine of that, it should be 1. It should come out 1. So then it should come out 1 plus tangent theta, tangent of 23.5. So then it should give you what you had, number of hours of sunlight on June 21st. So we could use this on any day. So I did an example here already. I said, let's assume the day is December 1st, and it's approximately the 334th day of the year. 334th, because after that you have 31 days, so that gives you 365. Okay, so again, approximate answer for T is 334. Okay, and let's say you live at a latitude of negative 25 degrees. So you would put here negative 25 degrees. Okay, so when you're doing this, you got to be in radian mode. When you're doing this, you got to be in degree mode. Or you could change degrees into radians. Or if you want, you could do here degree mode also, 360 degrees. Because the sun goes 360 degrees in 365.25 days. And that way you could stay degree mode, you don't have to change to radian mode. Okay? So you're going to have, this is negative 0.941759. Okay? Then if you multiply that by 23.5, you're getting negative 22.1313 degrees. Now what is that? That's giving us the deck angle of the sun on that day, the December 1st. Remember, it's gone up June and then September. December 21, the sun is going to reach the lowest position in the sky. And then December 1st is going to be roughly here, right? So that means the sun is on its way gradually to getting the most negative it's going to be, which is negative 23.5. So it's negative 22.13. It's only a degree and a half away from its lowest position in the sky. So then I'm going to take the tangent of that, tangent of the answer, okay, which already gives me a negative, right? Then I multiply that by tangent of negative 25, which already is a negative, times tangent of negative 25. So this is negative, and it gives you 0.189. So negative, negative is 0.189. You add 1 to that, 1.189. 1.189. You multiply that by 12 hours, 14, okay? 14.2757. So you have more than 12 hours of sunlight if you're below the equator. If you're above the equator, positive tangent of positive 25, this gives you negative times tangent of positive 25, it's going to come out negative, right? Negative times positive is going to come out negative. So then you're going to have less than 12 hours of sunlight. How trig and some analysis of geometry and our knowledge of the ecliptic helps us to analyze the number of hours of sunlight during the day for any day of the year, for any year. Thank you very much.